In this video, we're going to evaluate limits using infinite series. We're going to represent the limit function as an infinite series and then analyze the limit from the perspective of the infinite series. And so this is just another potential application of series. If for some reason you can't evaluate a limit by normal means, you could try a route like this. Okay, so let's first represent this function as an infinite series. So we have natural log of 1 plus x here, minus 1 to the n minus 1 times x to the n over n. Okay, so we can write this as, let's do x over x squared. So that's 1 over x minus 1 over x squared, then times the infinite series natural log of 1 plus x, which is actually going to start at 1. Okay, so this is okay, x to the n minus 2 over n. Now, this isn't a power series anymore because the first term is x to the minus 1. It only becomes a power series at when n is equal to 2. But I'm looking at the solutions manual, and this is how the textbook does it. So we weren't taught in the textbook about the idea of you could take any power series that you've proven that so like we've proven that we know the natural log of 1 plus x is equal to the sum from n is equal to 1 to infinity. Okay, now I was under the impression that you can't just multiply both sides by any function of x and say for sure that the equality still holds, because this needs to be a power series after you've done the multiplication. And up to this point, I haven't come across any examples from the example problems or in the book where they do something where they multiply both sides by something and it simplifies to something other than a power series. But here's an example where that is the case, and they still are saying that it's not like you can multiply a power series by anything and simplify, and that multiplication is valid. It's just about, can you still say that this equality holds without having to go through the official proof that the function is equal to the power series? I've talked about this before, but I don't want to get too much into it now. Just be aware that we multiplied this 1 over x squared, and now for n is equal to 1, this technically by definition isn't a power series, because the first term is not x to the 0, or it's not a positive integer or x to the 0. The first term is x to the minus 1. That's not by definition a power series anymore. We would have to take out that first term, then we'd have a power series. And so we weren't told officially if we had proven that natural log of 1 plus x is equal to this power series. And as long as you multiply both sides or divide both sides by something that results in a power series, then the equality still holds. Well, here we don't have a power series anymore. How do we test this to see if they're equal? So that's a topic you could do your own research on, or maybe I'll make another video about it, but just be aware of that. Okay, so now here, let's see. We can write this as, let's do this. So 1 over x minus, well, actually, let's do this. So the first term is going to be positive. Let's see, do I have this right? Yeah, this is right. So if we change this to just n, so then we could do that, right? Because but before you applied the minus and it switched all the signs, but now we just switched all the signs here and removed the minus. So, okay. Let's write this out. So let's write the series in the other format where you've got, so when n is equal to 1, we've got, it's going to be x to the minus 1 over 1, so it's going to be minus 1 over x. Okay, and then we'll get plus x to the 0 over 2, so plus 1/2, and then minus 1/3 x, and then plus 1/4 x squared, and then minus 1/5 x cubed, and then, okay, so we can see that this becomes, these cancel, this becomes okay, and this is, we can write another sum. Let's see if we can start at 0. Why not? So we've got n plus 2. Well, let's put the, okay, let's put, the first term is positive. Okay, now x to the n. Okay, now, but really we didn't even need to write this, because what we're going to do is so what is the limit as n approaches, or as x approaches 0 of this, and we want to come, the way you do this is you write it out, you write out the summation like this. So I mean, we can just, to make this mathematically complete, we can rewrite it as right. This is what we're effectively doing. We found the power series representation of this, which I guess is equal, even though it resulted, well, wait a minute. Once we did the full simplification, this is a power series for all n. So I guess that's why this is valid. Yeah, so in the intermediate step, we got something that wasn't a power series, but in the end, we did operations, and in the end, we started with natural log of 1 plus x is a power series. We subtracted that from x divided by x squared, and we ended up with a power series. So I guess that's why you can go ahead and say that these are equal. This is the power series of this. So, okay. But the idea is, so we're doing this limit, and the way you do it with limits, with power series, is you actually, you write out the power series like this. Okay, so I mean, I'll go ahead and erase this here. And you can see as x approaches 0, what's the limit? It's going to be 1/2. Right? That's it. Now, I'm just curious. I wonder if this limit, for some reason, does the calculator give us trouble? It shouldn't, because even the calculator could potentially apply it as a series. So I don't expect this to be an issue. X minus natural log of x. Okay. Store this as e. Limit as x approaches 0 of e is 1/2. You know, maybe this limit, using the standard limit techniques, maybe you can't evaluate it. You know, not even using L'Hopital's rule, there's no way to evaluate it, but maybe the calculator has like a programmed in it, like an if-then statement in it. If you can't evaluate with normal means, then it goes to the power series technique. Okay, let's represent this as a power series. So sine of x minus, starting at 0, minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. All right, so sine of x minus x plus so okay. Minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial minus x plus okay, so let's do this. Let's bring in, so okay, if we distribute the x to the 5th to each term, you get, we could bring out front here 1 over x to the 4th plus, and then this would be 1, okay, then that would be 6x squared, like that, okay, and then plus okay, x to the 2n plus 1 times x to the minus 5. That's going to be x to the 2n minus 4. Okay, so we've got plus, okay, when n is equal to 0, you've got x to the minus 4 over 1 factorial, so it's just, and it's positive. Okay, when n is equal to 1, this becomes negative, and you end up getting x to the minus 2 over, let's see, it's 3 factorial, so that's 1/6, like that. Okay, and then plus, and we can actually, I mean, we see these are going to cancel. So we can just go ahead and do this. N is equal to so, okay. There we go. Okay, and yeah, this isn't a power series, but once we've done simplifying, when n is equal to 2, you've got x to the 0. So this is a power series. We started with a power series. We did all kinds of side algebra, and we got a power series in the end. So we can say that these are equal. This function is equal to this. Okay, so if we write this out in the expanded form, when n is equal to 2, you've got x to the 0, and then minus 1 to the 0. So 2 times 2 is 4, plus 1 is 5. 5 factorial is 120. Okay, and then minus, and you've got 2 times 3 is 6. 6 minus 4 is 2, so x squared, and then you've got 2 is 4, plus 2 to 3 is 6, plus 1 is 7, so it's going to be 7 factorial, and then x to the x squared, and you know, that's all we need to do, because every term is going to have an x in it. So, you know, let's go ahead and put, so this is the limit as x approaches 0 of the sum from, and we could actually change this if we want to make it cleaner. We should be able to say, so when n is, we can start at 0. So if you're starting at 0, we still just do minus 1 to the n. And then, so when n is equal to 2, you've got x to the 0. So we want just x to the n. Okay, here when n is equal to 2, you've got 5. So here we want, well, okay, this is actually, this is every, it's skipping 2 every, like, okay, so when n is equal to 2, you've got 5. When n is equal to 3, you've got 7. When n is equal to 4, you've got 9. So we want that same idea, but we're going to do this. We're going to say, so we're starting at 5, so we're going to say 2n plus 5 factorial. That should work. When n is equal to 0, you got 5 factorial. When n is equal to 1, you've got 7 factorial. When n is equal to 2, you've got 9 factorial. Yeah, so that's a little simpler, right? We have x to the n. So, okay. Okay, and so what is this equal to? Well, all the x's go to 0. It's 1 over 120. Okay, so we're gonna start with arc tangent of x. That's the sum from n is equal to 0 to infinity minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Okay, so we've got x cubed minus 3x plus 3 arc tangent of x over x to the 5th is equal to x cubed minus 3x plus 3 so minus 1 to the n, x to the 2n plus 1 over 2n plus 1. Okay, all over x to the 5th. Okay, so now let's do this. X cubed divided by x to the 5th is 1 over x squared, then minus 3 over x to the 4th, then plus 3 times the sum from n is equal to 0 to infinity. Okay, x to the 2n plus 1 times x to the minus 5 is x to the 2n minus 4. There we go. Okay, so this is 1 over x squared minus... Okay, now let's just do this here. Okay, when n is equal to 0, you've got, it's a positive here, positive, so it's positive 1, x to the minus 4 over 1. And so with the 3, you get, okay, minus, and then when x is equal to 1, you've got what? 2, so x to the minus 2 over 3. However, you're multiplying the 3. So, okay, then we've got, so okay, we see these cancel. They subtract out, and then we're left with 3. Oh no, this could be equals 2 to infinity of okay, now let's change this to, okay, we'll bring in the 3. N is equal to 0. All right, minus 1 to the n. And then, so when n is equal to 2, you've got x to the 0. So it's going to be 3x to the n. And then when n is equal to 2, this is 5. So we want to do 2n plus 5. Okay, so there we go. So that's what we're doing here. We're taking the limit as x approaches 0 of the sum from n is equal to 0 to infinity okay, now let's see. We've got, when n is equal to 0, what do we have? This is positive. X to the 0 is 1. We have 3/5. Okay, when n is equal to 1, it's a minus. You have 3 over 7x. When n is equal to 2, you've got 3 over 9 x squared. When n is equal to 3, you've got 3 times 2 is 6, 3 over 11 x cubed. Okay, what is the limit as x approaches 0 of this? Well, all the x's go to 0. This ends up as 3/5. Now, I do want to point out that, you know, if you're not technically, we should have been checking the radius of convergence as we went, and just to make sure that the limit that we're evaluating is within the radius of convergence, right? If we can't do the limit of a power series as x approaches something that's outside of the, or not the radius, but the interval of convergence. Technically, we should have been checking. However, you can think about how it might be kind of difficult to do a limit that where x is approaching something other than the center point. But still, maybe you could do that. You could think about it like from a partial sum standpoint. You could get an estimate for the limit, an accurate estimate for the limit, right? You plug in an x value that's not the center point, and then that results in an infinite sum, and you do the partial sum, and you get the limit that way, which is fine. But in that case, though, just make sure that the x you're approaching you have to make sure it's within the radius or the interval of convergence. And so for all of these, what we would have done is we would have just had to do the ratio test, because to me, once you're subtracting out this from x and dividing by x squared, you can't really say that it's the radius of convergence hasn't changed from the base series, which isn't a big deal. You just need to do the ratio test on this and this, etc.